Hello everyone, and today we're going to have our next lesson on electricity, and we're going to focus on something called Ohm's Law. Up until this point, we just have that basic understanding of electricity, generally what is it, and AC and DC current and how those function. So with Ohm's Law, there's a few things that we're going to have to define, and so we're going to look at some of those key vocabulary terms. So there's three main pieces that are part of Ohm's Law. There's voltage, current, and resistance, and they all work together, which ultimately form Ohm's Law. So let's look at these three individual parts. The first one is going to be voltage. So voltage can be thought of or defined as the amount of potential energy between two points on a circuit. For me, that's always kind of felt like a definition that's like, okay, but what does that mean? It's kind of one of those definitions. So here's an analogy for you. The voltage can be thought of as the pressure of water in a hose, and so the more pressure we have, the more potential. All right, and so that image on the right, where we see that we have this water tank, all right, and then we have it feeding into the smaller pipe. This larger water tank that we have up here is holding a bunch of water, which in this case is like our charge, our electricity. Okay, the water is kind of the electricity that's flowing. Now, the fuller this container is, the more pressure is ultimately created as it is getting released from the bottom here, right? You can kind of think of this top part as a battery. It's a little bit like a battery. And as this, gets drained, so as this water level gets lower and lower and lower and lower and lower, this pressure gets a little bit lower and lower and lower. And that's why you tend to see if the batteries are dying on something, they tend to be getting a lower charge. So they may not work as effectively, right? So if it's a flashlight, maybe it starts getting a little bit dimmer. Sometimes that means, if it's a remote, maybe it takes a few extra clicks to get it to work because there's just not quite enough power and you have to wait till, it enables to kind of like skim. Oh yeah, there's the power. It kind of sputters out almost kind of a thing, right? And so that's what's ultimately happening here. So essentially, the bigger this top part is, it allows us to get more pressure within essentially the wiring, which is happening here. And now, the reason we have this kind of piece bracketed here is really, in this scenario, if we were to create this bigger spacing, right? So between these 2 points, that creates a greater amount of potential energy between those points. They want to, it wants to resolve this charge difference. Everything wants to resolve that charge difference. And so as they don't like to be uncomfortable effectively. And so what that means is we have this big difference, just like when you have like gravitational potential energy, that like that height, that distance mattered. It's a similar thing with this. And that's why this piece is important, really. So if there's a really big charge difference, that's where we can get this sudden burst of energy, and that's actually where we'll get that static coming from. We talked about the static discharge. Actually, there's a pretty high voltage static discharge. But usually if it's when you're shocking, your friend or, like you have a fleece and you can generate that static, it is a really low current, which we'll talk about in a second, but it can actually have a pretty high voltage because it's got a whole bunch of potential energy being released all at once, right? So that's kind of what current voltage is. Hopefully that makes sense. We'll continue to work on it in case it's still a little foggy. I think voltage conceptually is one of the harder ones to fully get. And then with voltage, voltage we measure in a unit called volts, and we cleverly use a capital letter V. All right, so let's talk about our next one. Our next one's going to be current. So current is the flow of electrical charge. The higher the rate, the greater the current. Now I find current tends to be one that people understand a little bit quicker just because the analogy with water is very similar, so the amount of water traveling through the hose is going to be the amount of current. And so we have a similar image on the right in which we have our reservoir of water, and then we have it flowing through a tube. Now, one tube is roughly twice the diameter of the other tube, and you'll see the one that's wider is going to have ultimately, let me get my pen tool here, is ultimately going to have more current because more can travel through it, right? Sometimes people call this like a bottleneck, in which you could kind of think of if we're all trying to go through a really narrow hallway, right? All these people, they can only go so far, but find it's just your shoulder to shoulder, and you just can't. More people can't go through, right? Just like if we had these buckets, we had one with a big hole, one with a small hole. Well, the one with the big hole is going to empty faster because it's able to have more travel out of it. And it's the same thing here. We're going to have a lot more of this energy traveling than in this one, where it's just going to be a lot less, right? So that's actually the part that makes electricity potentially deadly or harmful, is the overall current that something has. If it has a really high current, it could still have a fairly low voltage, but because there's just so much of that electricity traveling, that's what actually overwhelms, in this case, like our nervous system and things like that. And we measure current. So current, we measure in the unit of amps. And I didn't put it in here, but you can use a letter A for measuring in the amps. A lot of people also like to just write out amps for what they can do for that as well. All right, so let's clear that off. And on to our third one, and that's going to be resistance. So with resistance, it's the amount the wire or load. All a load is, we'll spend some more time talking about this when you get more into circuits. A load would be like a light bulb, something that's going to consume that electricity. So it's the amount of wire or load, amount that they resist the flow of electricity. All right, so the general analogy, a narrow tube would resist water more than a wide one. All right, and so we can see that shown on the right, where if we have one that doesn't have any sort of pinch in it, right, it's free, it can just keep traveling. If we have one that does, again, we have this point where only so much can actually travel through. So a couple of things actually with this, some important pieces to mention when it comes to overall resistance. And really what that is, so there's a couple of other things that will ultimately impact our resistance. So the first one is our resistance will increase. So our resistance is going to go up if our wire is going to be longer. So the longer our wire, the greater our resistance. So if you have a bunch of really long wires, that's going to ultimately create our resistance along within the circuit. Another one is as the wire gets thinner. So I think this is the one that is the clearest and generally the most impactful. If a wire is really thin, it can only have a certain amount of current traveling through it, partly because that resistance is going to really clamp it down because, again, it's super, super narrow, and so things can't travel. And the last one is going to be as it gets hotter. Okay, so as things things get hotter, they're just becoming inefficient. Heat in general is an inefficiency. And so part of the reason why as they get hotter, we get our resistance increasing is because that wire is going to, there's like some thermal expansion. And so what that does is it doesn't allow the electricity to flow as readily through it, as because we get kind of this expansion, and that kind of creates this inefficiency as a result. So just kind of the general rule of thumb to keep in mind with resistance, the longer, the thinner, and the hotter the wire, the reduces the overall amount of current that can travel through the wire. All right. And for resistance, we measure it in we don't use R. We can't use that because we use R for other things. And so we actually are going to be using the unit ohms, abbreviated with our fun Greek symbol there, omega. So that's where that is coming from. So that's the unit we're actually going to have for our resistance. All right, finally, let's define Ohm's law. So our last little part. So Ohm's law ultimately defines the relationship between our voltage, resistance, and current. So they all kind of work together. And so, as one thing's increasing, that can decrease something else. And so they kind of all have to work together. And so we have V in our equation representing voltage. Now current gets a little tricky because we abbreviate it with an I, because we're running out of letters in our alphabet for equations, so we actually use I. And then sometimes where that I comes from is sometimes you'll see, if you look at headphones or different speakers, things like that, you'll see them listed with a recommended level of impedance, and that's where that's coming from, and that's just another way of looking at the current, and that's where that I is coming from. So it's actually still connected to current, just not in a way you would expect. So that's sometimes what's tricky about a lot of these, is just keeping track what abbreviates to what. And finally, we have resistance, and that's going to be, it's with an R for resistance, right? But then we use the unit, not R, don't use R. It's going to be, again, that omega Greek symbol. All right. So if we look at our triangle on the right, we've used some of these in the past, in which so our voltage is going to be equal to our current multiplied by our resistance. So overall, our voltage, so the greater the current and the greater the resistance, is actually going to increase our voltage, which is our potential. Okay. And then if we have our current, so now we're looking on the bottom left-hand corner, is now going to be the voltage divided by our resistance. So as our, basically with our voltage, the smaller our resistance with our voltage, the greater our current, which makes sense, right? So if we have a really high voltage and a really low resistance, we can have a really high current because that is going to be able to easily flow. And that voltage is that potential. So the resistance holds back that potential, right? Voltage is like, yeah, let's go, I'm ready. And then the resistance is like, okay, I'm going to hold you back. And that reduces that overall current. Okay. And then our resistance, we have our voltage divided by our current. And so with our resistance, so again, we have our voltage. Now, if we have a really big current, that's going to mean that we have a high resistance, right? Or sorry, that's going to reduce our overall resistance. If we have a really low current, then that's going to mean that our resistance is going to then be going up, right? Because we're dividing by a smaller number, meaning if we have a lower overall movement, that means things are being pretty heavily resisted. So that's that kind of relationship. So if you have any questions, let me know. That's Ohm's Law, and then we'll continue to kind of practice with it. So have a good one.